We are now going to see how distribution theory is applied in real life. For practical examples, so how do we use distribution theory? So we start again. So we'll use the real life data. We'll so create the workspace. And in the workspace, there's a file called rainfall. Okay, there's a file called rainfall, which I will then download using the command read.csv. It's a CSV file. It has been read. Then I'll see what are the variable name in the file. And I've got a whole lot of variables. I'm not really interested in them. And what I'm really interested in is the district. And then I'm interested in the total annual rainfall. Okay. Now I want to know how many districts are there. So to get the variables in a the levels in a particular variable, if I want to know what are the unique cases in this variable called districts, then you use the command levels. So to know So I want to know what are the districts that are there in the data. So what I do is I say levels, name of the file is RF, and I get districts, and I get these are the districts that I get. Okay, then supposing I'm interested in getting Bagalkote. I want to subset this data because the data is very big. So what I'll do is I will create a new variable called Bagal K. So I'm going to subset this data out of this file called RF, this file which I read, which I call RF. I open a square bracket whenever I subset, and then the name of the file, the variable name which is district. Okay, and then I say equal to Bagalkote. So what this command, subsetting command, will do is it will extract data pertaining to Bagalkote. Yeah. So remember, Bagalkote is a text, so I have to enclose it in inverted commas. So it is RF, name of the file, into name of the variable equal to Bagalkote. Close the square bracket. Before quoting, I must put a comma to indicate that all the columns in the data set have to be included. So I now run it, and then I can now view it. And view it. And there I get the data. So I get data only of Bagalkote. It's a subsetted file. Data from 1950 till 2014. Okay. The next what I will do is I will get a plot of this data. Plot. Now the name of the file is Bagal K. The name of the variable that I want plotted is the variable called annual rainfall, which I have it here, which is the annual rainfall, which is a cat. Okay, then I say type is equal to line and color. Color is equal to maybe green. Right? And then I run it. Then I get the rainfall of Bagalkote in the last so many years. That is, you can see there is an increasing trend. There's an increasing trend to the data. And what I would then do is I will put a title also. Main equal to trends in rainfall in Bagalkote district. And now I get a plan. I get the title also, I get the annual rainfall, and the data is available for different years. So I have a database which is now going to now tell me what is the pattern. Now I want to know what is the distribution of this rainfall. So what I'll say is hist and get the rainfall, and then okay, so I get a distribution. Now once I get a distribution, I need to know what is the type of distribution. So the same thing I've done for Chitradurga, right? So to know whether it's normally distributed, what I will do, we do a skewness of this variable Bagelkote. And if it's 0, then it's normally distributed, not very normal. It's tendency to be a little skewed, and therefore, it takes a little, it's not normal. I'll repeat the same thing for Chitradurga. Okay, same way, what I do is I give the name of file called chit. I do rainfall, same way, and this time I extract Chitradurga. Then I've done the same thing for Belgaum, I've done the same thing for Gadag, I've done the same thing for Dharwad, done the same thing for Kolar, I've done the same thing for Tumkur, Bellary, Kodagu, Dakshin Kannada, and a whole lot of other districts. Right? Now I want to know which distribution does it follow. I've got data now. I have got data. But I want to know which distribution does it follow. So I'll do the other one also. I'll do what is called as plot density Bagel annual. Okay, there it is. Quite a peaked distribution. And now I'm not sure which distribution it follows. I'm not sure which distribution it follows. And I need to know which distribution does this follow. So R has a program which is called R has an option. So we have already downloaded this earlier. I'll just copy that and take it to the top. Okay, we are working with Bagelkote, right? Just push that down. Now we've already downloaded this library Vista Plus for some of our operations in the previous lesson. I'll anyway install it once more because every time a session starts. And now for the Bagelkote annual rainfall, I will invoke this program. And then I will use this word describe distribution Bagelkote annual. It's not discrete, it's continuous. Therefore, I say discrete is equal false. And here I get a result. Now, my observation lies somewhere over here. Right? So, when it lies somewhere over here, if it were here to be here, it would be a uniform distribution. If it were here to be, it will be a normal distribution. So, it is somewhere between a normal distribution and a logistic distribution. It falls somewhere over here. Okay, so it looks normal, but not actually normal because the kurtosis is very large. Because it's a plot of skewness against kurtosis. So skewness is 0, kurtosis is not 0, and therefore the distribution, it's able to identify the distribution. Now you could do this for all the other variables to find out what distribution it may follow. Now if you want to see the same thing if you want to see for Chitradurga, so just copy this data, place it over here, right? And take chit. Instead of Bagelkote, use chit, because that is Chitradurga. And place it and run it. We get another one. Now Chitradurga is here. Now Chitradurga is exactly normally distributed. So it's overlapping. So this option helps you to find out what distribution your data is likely to follow. Okay, you could try this out with more distributions. And once I know it follows the normal distribution, then my job becomes very easy. I can use it. Now for Chitradurga, now I've got a, I'll do a density of Chitradurga plot. So Chitradurga is a very normally distributed. You can look the graph, you can see, if I'm interested in finding out what is the probability that Chitradurga yields will fall below, I'm sorry, rainfall will fall below, say, around 480, it's about 80%, 480. What is the probability that Chitradurga rainfall will fall below 480? So I will use what is called as P norm, P norm. So P norm, annual. I do not know. No, it follows normal distribution. So I want to know what is the probability it will fall or below 480 millimeters per day. For this, I should know the mean because it's normally distributed. Mean Chitradurga, and of course standard deviation is also. So you give the value that you want the probability for, the mean and the standard deviation, and you run it, and you get a probability of 0.23. So what it says is, okay, I showed you this yesterday in the previous lesson. So the probability that the rainfall in Chitradurga will fall by 20%, that is from 100 to 80, this is less than 80, this probability is given by this number. You can directly get. So that is why you should know the distribution. You should know the distribution. Okay? Probability is 0.23. So there's a 0.23 probability that rainfall in Chitradurga will fall below 480 millimeters per annum. Now we can do the same thing for Bagalkot. So Bagalkot, it won't be appropriate because it doesn't exactly follow a normal distribution. So then, I can find out a lot of things. I can find out what is the probability. And then if I say, if the rainfall, what is the probability that the rainfall, given the probability, I can find out what is the rainfall. So what is, this probability, what is the 10% probability? I want to know what is the 10% probability if the probability is 0.1, what will be the rainfall? So I will use what is called as Q norm, and I will use 0.1, and then run it. And just a 10%, if there is the 10% probability value will be 397. So if it falls, what do you call, 80, 70, 60, or 10%, the 80, 70, 60. But if it's going to fall about 80%, the value would be roughly 400. In other words, what it's saying is, in this distribution, where will 10 value of 400? So 400. Now at 400, this area is 10%. It's 10%. So you can use the denorm option to find out, given a value, what is its probability? Given a value, what is the probability it will reach that value? Right? And okay, now we go to a little more advanced analysis, where we want the computer itself to decide what is the distribution. Rather than we deciding what is the distribution, we want the computer to tell me what is the distribution. For that, we use what is called as this. This is a very useful command. I just copy it over here, and I'll explain to you what exactly it's doing. Here, to determine which distribution the data follows. So this is the greatest challenge for any analyst. This is the greatest challenge for any analyst. What distribution does the data follow? Okay. So you can get it in from the net. So to determine that, you have to install the library called GAM LSS, and then you have to invoke it. Then you have to install the library GAM LSS.dist. That is also to be captured, and you also have to invoke this library called GAM LSS.add. So all these libraries, all these packages have first to be installed before you can invoke it using the library command. So once this command has been working, now I will take Bagelcode. Okay, the command is here. You direct the output to a file called fit, and then you use the command fit_dist, meaning fit distribution. Now this will not work if these three packages are not installed. And once these three packages are installed, then we use the command fit_dist, D with a capital D. Then we give the file name. So we'll take Chitradurga itself. Okay. And so if you want to know what this K type is real plus trace is equal to false, then you have to just say fit_dist, put a double question mark, and get information about it offline. It's an offline help. So fit_dist, okay, fit_dist will give you all the information that you want. Fit_dist data distribution. This is a characteristic name naming the distribution for which the corresponding density function D name, the corresponding distribution function P name, and the corresponding quartile functions Q name are to be defined. So you can define the distribution if you want. Okay, if you're specific about the distribution, then it tells you which method it follows, whether it follows a maximum likelihood estimate, or whether it follows a method of moment estimation, or whether it follows a quantile matching estimation, or a maximum goodness of it estimation. So one of the three, four measures you could use. Otherwise, you could also keep it as default. That's a method. So dist star. Oh, sorry, I think I made a mistake here. Not exactly that. We have invoked it in univariate design. With distar plus. Yeah, that's the one. So we press it again. Yeah, meanwhile, we'll just be working with this. So you give the variable name. Okay. And we go down to the bottom and we will get a help. So it will fit a gamma distribution and it will give you the parameters. Okay, this mistake is not that. It's not that which I wanted. Okay. So it will fit the distribution. Now you will just see how this works. This is slightly different. Fit_dist. It is fit_dist actually. Fit_dist. It is fit_dist, and you can just see that. So it will tell you which is the distribution that this data follows. Okay. So I'll run this. Show some error because the data has to be very, very characteristic. And it fits a distribution for you and says it's a Weibull type 3 distribution. This is not exact. So there are many variants in distribution. It's not only the basic, the ones that you described so far are the basic distributions. So there are many variants. For instance, we will discuss a Weibull distribution, but there is a distribution called Weibull 3, and we can get the information about this from the net by just pressing that distribution, and you get it. You get all the details about the distribution. It's called a discrete. It's a Weibull 3 distribution, and it gives you all the details. Weibull 3 distribution is a probability mass function of a quartile, or that details. And he says you can run a Weibull. You can, once you know the Weibull 3, you can just use, rather than using a normal distribution, you should use these parameters, like so we'll take to the Q now. We'll know the P norm. X is the value. We'll just do the P norm like we did over there. So just like we can generate the distribution if you like. But the interesting thing is it uses the beta. It uses the beta. Oh, it's taken a value 0.75. These are the parameters of the distribution. You must find out the parameters of this distribution first. So before you can use it, you need to find out the parameters of the distribution. We just did it. Fit the star. We did it earlier. In the earlier class, you would have noticed. We did that. Fit the star. Fit the star, like we did over here. And for fit the star, we should use I'll copy this and show you how you get the parameters of the function that we just estimated for Chittathura. Okay. B3, I will call it. Now if you go and get there. Okay. Data is Chit Daniel. Okay, that's the details we do not have. Anyway, we'll discuss that later. We'll discuss that later. But using this option, GAM LS, GAM LSS dist and this, we can find out which distribution does the data follow. So I'll hold this for a while. Because it's not exactly that simple. So I'll just show you how this is done. So like that. So now we've run this, and we found out that the Chitraturga follows a Weibull type 3 distribution. It's called VE3. So the details we had over here, we can just show you. It's called. So for this, you should go to Google and get the help. Okay, you must go to Google and get the help. Yeah, so here we will type 3, so they call it. Weibull 3 parameters. So there R has got this option. We just saw it a little earlier. And He says we can get it with dp vbull, get the parameters of the distribution, and you get all the details about the distribution. It has got, uh, you know, it has got a shape parameter and a scale parameter. It's got a shape parameter and which which I've shown you how it can be estimated using other distributions. So I won't get into that because it lets me get into any kind of difficulty. So using this command, we could find out Chitraturga is following. Uh, when we described it, the thing we said, we found out that Chitraturga is absolutely normal, right? And then we went a little further and little refinement. When we went a little refined, we were able to find out that it actually follows a gamma 3 distribution. Now let us do the same thing for Bagelkot. Let's copy this, put it over here, and we'll change the file name to Bagelkot. Okay, so now we'll find out what distribution set does Bagelkot follow. Right? We go here, we run it. So it makes our job easier and easier. You can see, and when I get the summary, it tells me, look, these are the two parameters of the distribution, and it also, this follows a Weibull type 2. So you can see how, to what extent of refinement distribution theory gets, from the very basic that we showed you in Excel to the very complicated. So once I know this distribution, then I can use that options like Q norm, B norm, I just showed you. So you can find out all the calculate. Now we had a Weibull 3. So for the Weibull 3, if we are interested in finding out what's the probability that these things are going to follow less than a particular value, then we will just copy this command. We'll copy this command here. And substitute the values from the data and calculate the probabilities, which is the main thing that we're interested in this thing. So if you're doing a p distribution, we'll find out what is that value I want. So I said 500, and then the shape parameter I get from here, Bagelkot, here, Weibull 3. So Weibull 3 is for Chitraturga. So Chitraturga came earlier. Here it is. So the shape parameter, I will give this, and the scale parameter and you run it, and you will come to get the probabilities in a very convenient way. So now one has to be familiar with all the distributions and then be able to use it, in a very effective way, because the future, when you're talking about machine learning and artificial intelligence, probability distributions play a very important role. And one has to be very precise, because if you assume a normal distribution and the data is actually a Weibull 3, then your probability values are going to go wrong, because you're going to use mean and standard deviation, and rather than the correct parameters. So this is the completes my presentation on distribution theory.